So November, so Monday, no, Tuesday. Next Tuesday is the test, right? Test number 2. It has the same weight as test 1 on the final, 20%. It's going to be the same format, right? Multiple choices and 20 questions in Canvas. No, that will be for the other class. Okay, so you need to bring your equation sheet this time because it's not embedded, right? So you need to know your equation sheet. It's only everything Newton. So it doesn't include that unit. That unit is a new unit. This unit will be for test number 3. Test number 3 is going to follow not very far from test number 2, and it's going to be online, and I will open a window at night, like 4 hours window, because people are going to say, oh, I have a job, oh, I'm going to class, oh, blah, 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 blah. So it's a 1 hour test, but I will open a 4 hours window. Okay, it will be at home. Okay, for test number 3. Okay, and in person on paper, it's better to come for test number 2 because it will be very close to the tutorial that you have in Dropbox, except for conceptual questions. Conceptual questions, you can use the pop quizzes, take screenshot. If you have to take the MCAT, you have to be very organized. Like you have to make folders, like folder Newton, and then you put all the pop quizzes inside and all the prep that you do. Okay, because it's not an easy exam. So anyway, that's all I had to say. Slide 31. So I have extended the homework, advanced Newton. That's not going to be, I mean, the most advanced one is not in the test, but it's important for those going into mechanical engineering or civil engineering or physics, or those kind of majors. Okay, so we stopped here. So we are doing work. So work is energy in transfer from one system to another system, right? So if work is done on a system, the kinetic energy has to change. Okay, if the kinetic energy cannot change, that means there is no done. And then the energy work theorem says that the net work equals to the change in kinetic energy. So work is energy in transfer. Okay, so for example, if you have frictional forces, they do negative work because they are taking away energy. So if we forget about the dot product, but we should not forget, but to simplify, work is force times displacement, but you have to take the parallel component of the force along the displacement. Okay, so we did that last time. You can say if the work done or by a force, so the work done by a force on a system, okay, will be equals to the parallel component of the force along a displacement, so delta x, for example. So we take only that component here parallel to the displacement. And the net work, okay, so that will be equals to the net force times displacement if it's moving along the x, for example, and that will be equals to the change in kinetic energy. So final square minus initial square. And I told you that if you massage that a little bit, then you get your kinematic equation, right? That kinematic equation here. It's the same thing. If it's along delta x, and here we have that the net force equals mass times acceleration. Okay, so we did that, and then so this is very interesting. So I highly recommend that you open your textbook, you try to work on that on your own. But what is interesting is that you have a trade-off between the distance and the force applied. So the same thing like when you have a hammer here, right? you see here, if you cannot apply a very large force, you're going to increase the distance. So it's like a trade-off between the force and the distance. So here, if you have a very large distance and you don't apply a very large force, so you're going to have a small force over a very large distance will be equals to a huge force over a small distance, because the nail here has some resistance, so it's not going to go a big distance here, right? So the force applied will be huge, and that force applied will be just the normal force, okay? So normal force is just how hard the surface is being squeezed. So the force applied to the nail will be the normal force, because you push on the nail will push back on you. So this is called a machine, okay? It's a force multiplier. And when you have a force multiplier, there is always a trade-off between the force and the distance. Okay, so we already have seen that with the pulley. If you remember the pulley, pulley somewhere there, here. See, there is a trade-off. So this is a force multiplier, and there is a trade-off between the distance the load is moving and the effort. If it's a force multiplier, so it means you are 4 times stronger, okay? So it means if this is 200 kilogram, you just have to pull divided by 4, so it's 50 kilogram, okay? But the distance that you have to pull is 4 times more than this, the load. So the load is moving by 1 meter and you have to pull 4 meters. So it's a trade-off. Either it's a force multiplier or it's a distance multiplier. So when you are doing biking, it's the same thing. Either you multiply the force going up or you multiply the speed, you increase the speed. So there is no free lunch. That's the idea, right? So no free lunch. And okay, we're gonna have a pop quiz today. So this is a very famous movie, of course. I was not born at that time, okay? Don't go think that I was born. That's a 1933 movie, very famous movie, very, very good movie. For the time, it's a very impressive movie. So it's King Kong from the first one, 1933. But if you time how long it takes to go down, they did a pretty good job. So the idea is that it's not the fall that kills, it's the landing. Okay, because all this distance here, huge distance, 500 meters, I don't know how big is the Empire State Building, all that distance here, okay, it's gonna hit the ground, and the ground is gonna go in, so King Kong will go in the ground by a very small amount, so the force that he will experience will be huge, million tons, right? So it's not so much the falling as if you don't land, you're fine. So manage not to land and everything will be fine. Okay, so that's why they use this technique in civil engineering. You see, you need to have some rail here to guide the load. And of course, it's going to introduce some friction, but not that much. And then the pole here goes by a small amount. So the force applied, the normal force, it's going to be huge. Okay, so we did that last time. So work and kinetic energy, so you can do that on your own. But let's say you are hitting the brake because you are about to have a crash. Very easy here. So all that kinetic energy. So here you have kinetic energy to begin with, right? So 1/2 mv square. And then if you hit the brake, all that energy, kinetic energy, will be transferred to heat. Okay, so you can still apply the equation here, right? So all that kinetic energy, you're going to have a change in kinetic energy that will be equals to the work done by friction on the car. And that will be heat. Okay, it's gonna be negative. So all that kinetic energy that the car had, when it's going to stop, all that kinetic energy has to go somewhere, and it's going to be transferred by the work done by friction into heat. Not only, and if you have a crash, it will go to the noise and damaging your car, all that, right? So you see here the change in kinetic energy, if you stop, will be the final speed square minus initial speed square will be equals to the work done by friction. It's negative, so negative the frictional force here times the times displacement. Okay, so that will be the frictional force times the displacement. So you apply the same equation here. Okay, so that's what they did here. The work done by friction, okay, will be the work of friction, the force of friction times the displacement equals the change in kinetic energy. So from that, you can find how long it will what's the distance before the car will stop. Okay, so that's why you need to keep your distance. You need to keep your distance because kinetic energy is proportional to the speed square. So it's a killer. It's huge. Okay, so the distance here has to be large enough if you do not want to crash. Is that clear? Right, so this is the kinetic work principle or theorem. The work done by a force equals the change in kinetic energy. Work done, the net work equals the change in kinetic energy. All that kinetic energy is going to turn into heat. So I'm not going to do it because you can do it on your own. It's not that hard. Just plug in. Okay? Okay, and here, what do they want? They want to see. So now the distance here is not large enough, so it's going to bump into the car. So they want to know what's going to be your final speed when you're going to bump into the car. So you can do the same equation that you are using here, right? Except that the final velocity when you hit the car is not zero. You don't stop soon enough. Is that clear? Okay, so the work done by friction is the force times displacement equals to the change in kinetic energy. So kinetic energy is a killer. That it killed the dinosaurs, right? All that kinetic energy of the meteorite when it hit the earth. What happened to the earth? It came to a boil. You had fires everywhere. You have a nuclear winter for years, and all the dinosaurs died. Oh, which is good for us. I'm not going to cry. Right? Okay. Next, a little bit of calculus here. So far we have seen a constant force, a force that does not change with displacement, but in reality is not the case. So for example, if you start to pull a wagon, right? So first it's going to be small, and then you increase your force, and maybe you get tired, so it's going to decrease. So the force can change with the displacement. So you can do this, okay? So I pull, I get a boost of energy, I pull harder, and then I get tired, and I'm not going to pull as hard. Okay, so we need to change the equation a little bit. So if you have any question, let me know, right? So the work done by a force on a system, okay, we have seen it should be, if the force stays the same, it's just the parallel component of the force along the displacement times the displacement, and this is equals to the change in kinetic energy. if the force changes with x. Okay, so now you need a sum. Okay, you need to add all the little work, right? Remember, if when we talk about the network, okay, the network of the force on the system, you need to add all those little work done by the forces, right? But that means it's an integral. Okay, integral means sum. So it's going to be a sum, okay, from place 1 to place 2. For example, if you are along the x, and then the component is along the displacement, and that's a function of x dx. Okay, I'm just replacing a sum by a continuous sum. So integral means sum. That's all there is to it. Okay, so if you take calculus, right, sum is just integral. Integral means sum, so it's a sum. Okay? Is that clear? It's not advanced calculus, very basic calculus. So if you have the forces as a function of x, so from place 1 to place 2, the force is going to increase in magnitude, get to a maximum, and then it's going to decrease. Okay, so to find the integral here, it's just the sum of delta x times the force, delta x times the force. And you know that integral means area under the graph. So if you have a graph f of x as a function of x, you just need to find this integral here, this area under the graph. Yes? Right? Just a definition of integral means the area. So the work done will be this area here. Yes or no? So you say yes, yes. Yes, right? Okay, and do you remember Hooke's law? So let's go back to here. Hooke's law, it says that if you apply a force here, so I'm going to apply a force, of 50. So I'm applying a force of 50 Newton. So now you have a restoring force, right? The spring here is not happy to be stretched. It's pretty upset. And you say, here you have the applied force pulling. So you're going to have what it's called a restoring force. Okay, we call that the spring force. Okay, you're going to have a restoring force. Spring force. That spring force is trying to bring back the spring to its initial length. Okay, now more you're going to pull, more restoring force you're going to get. And the equation is very simple. It says that the spring force, the restoring force, will be equals to, I'm going to put a minus to say that you have to do work against it, minus k, it's the spring constant, times the displacement delta x. So it means that the stress is proportional to the strain. More deformation, more stress, more strain, and or more strain, more stress, right? So if you have a resistance band, you already know that. Like if I pull a little bit, okay, it's not going to be hard. If I pull twice as much, the restoring force will be twice as much, and the stretch will be twice as much. So if I multiply the stretch by 2, the restoring force is going to be multiplied by 2. It's very hard. Okay? So it's proportional to the displacement here. So that's going to be a spring force. Do you agree? You can see that here, let's say 55 Newton. No, I'm trying. Okay, let's show that. 50 Newton. Okay, what's going to be the displacement? That's going to be the displacement here. Okay, displacement is 25 centimeters. You have the applied force, and this is called the restoring force. Restoring force. He wants to bring back to the initial configuration. if I multiply the applied force by 2, okay, restoring force is multiplied by 2, and the stretch is multiplied by 2. Is that clear? Okay, if I divide by 4, so now it's 25 here, 25 here, I have 12.5. Is that clear? Okay, that's called Hooke's law. It's very important if you do engineering in material engineering, strain and stress. So anyway, that force here, okay, so let's say you have a spring, okay, it's happy, minding its own business, it's not being stretched here, has no complaint whatsoever. So that will be X. X, it's gonna be my stretch. Okay, now if it's gonna be stretch, here, delta X, that's gonna be the amount by which it's gonna be stretched. You see that, oh, not delta X. It's gonna be delta X, but I'm gonna call it X here, right? Because it's on the X-axis and I start from 0. You see that the force here, it's gonna be proportional to X. Do you agree? In magnitude, F equals Kx. So can you find the work done, okay, by the spring, by you on the spring? Okay, let's say this is the applied force. The applied force will be proportional to the stretch. So what's going to be the work done by you on the spring? You see that the applied force is is a function of x, right? So the applied force equals kx. So how can I find the work done? So I need to apply the definition, right? From 0 to x. Okay. And then you have the force. Do you agree? Delta x, right? So then what? Kx dx. How we integrate this? Hello. Huh? Kx squared over 2. Integral of x. Okay? So the work done, you are doing work. Okay? You are transferring your energy to the spring. That energy is going to go into elastic potential energy. Okay? This is called store energy. Okay? I'm using my ATP in my muscle to store energy, so I'm doing work on the spring. Okay, so that energy that I am transferring to the spring will be 1/2 kx squared, and this is stored energy because I can retrieve that energy. So if I let go, it's going to go into kinetic energy. So that will be, you integrate 0.5, thank you, kx squared. Okay, thank you. That's going to be the potential elastic energy. You are doing work on the spring, that energy goes somewhere. Okay, it's going to go into the new configuration. Now, if you don't know how to integrate, no problem. You remember that the integral means the area, or the work done is the area under the curve f as a function of x. So the area of a triangle is 1/2 the base, which is x, times the height here, which is kx maximum. So kx here, and you get the same thing, 1/2 kx squared. Is that clear? So if you have force as a function of x displacement along the x, all you have to do to find the work done is to find the integral under, the area under the graph, which is the integral. Okay, it's not that too hard. So here is a good example. If someone is using what is called a bar, right? So first it's gonna be small, then you increase, get to a maximum, and then you let go. So it's gonna go something like this. So if you want to find how much energy was stored inside that bar, then you need to find this area here, and you can use a technique or ask, it's called numerical analysis, right? You can find the area. So that will be more engineering. You need to have a sensor, and you see by how much it was stretched, and then you find the area here. Is that clear? So that will be the formal definition. The work done by a force on a system, you need to take the integral, and you have to go from position 1 to position 2. Okay, so here if you have a what is called polynomial, then that will be integration. Don't forget, that's even more, one more step. Remember that the force has to be parallel to the displacement. So someone asked me a question, it's not here today, but if you go from A to B, okay, and you apply a force for each little segment, so you have to decompose that path here in small segment dr. So a little segment here, okay, and for each segment you need to find the parallel component of the force along that segment. Is that clear? So that's why the formal definition uses a dot product, scalar product, right? A dot product, because that will be the component of F along that small displacement, and then you need to add them up. It's like adding work. Is that clear? It's not that hard. And here, actually, using this, we go back to the work energy theorem, using a little bit of integrals here, massage and shake it and massage, and yes, okay, so then you get to this. Okay, so you can show that the net work equals to the change in kinetic energy. So a network is done on the system only if the speed is changing. Okay, so you can do that. It's fun. It's math. You're supposed to be good at math. So this is fun to do. So I'll let you do that on your own. Example: if you have a spring, like using Hooke's law, and F equals kx, you see the force is going to change with the x. You need to find this area, and you get 1/2 kx squared. Okay, so harder you pull, more resistance you're gonna get. That's why it's called resistance band. You multiply the stretch by 2. Okay, the restoring force will be multiplied by 2. So the applied force will have to be multiplied by 2. So this is called Hooke's law. K depends on the spring, its cross section, how stiff it is. Larger K means stiffer it's gonna be. Okay, blah blah blah. So we already did that. Yeah, do a fast example. So this is for tires. When you are inflating your tires, you use a gauge, a pressure gauge. So the gauge is just how much pressure is inside the tire above the atmospheric pressure. So it's a differential. Okay, high. above the atmospheric pressure. So the way you measure the pressure here, you see you have a spring. Okay, it's the pressure gauge. You have a spring and all this air that are being compressed is pushing the spring. So there is a relationship between the amount that spring is being compressed and the pressure, because pressure is force per unit area. The area does not change. So you have a linear relationship between the pressure and how much is being compressed. So you just apply Hooke's law. There is nothing to stare at. Just apply. Oh, my knees. Just apply Hooke's law. There's nothing. It's interesting because you see how it works. So the gauge pressure is how much above the atmospheric pressure you get inside your tire. So you just let's do that just in magnitude. Just apply the equation. Yes. Okay. And the meaning of pressure, the pressure is a force per unit area. It will be Pascal, Newton, meter square. Okay, it's a scalar. It's not a vector. But the area here, we don't worry about it because it doesn't change. Question? Okay, so if you want to measure the spring constant, maybe you did that for the lab. So you have a spring here, it's in static equilibrium, up equals down. So the weight here, mg, that you know, equals the restoring force. So in that case, you are hanging a mass, right? So the applied force is the weight. That force here is the restoring force, so the spring constant. Up equals down. So you just have kx. X is the amount by which it's being stretched here, which is d. So k times d equals mg, and that's how you can measure spring constant. Is that clear? So there is a threshold. If you stretch too much, then you get to a point where you get deformation, and then you cannot go back. You have damaged it. Any question? Okay. So you can compress, you can stretch. The equation is the same. How much elastic potential energy is stored inside a spring is 1/2 kx squared if you start from zero deformation. So the unit for potential energy will be joules. We're going to get back to that. So talking about potential energy. So potential energy, very, very important. It's a stored energy, and it depends on the configuration of the system. So we always talk about the change in potential energy because you can choose the level 0 of potential energy wherever you want. Okay, so what matters is the change in potential energy. So any potential energy, example, elastic potential energy or gravitational potential energy. All those are energy that will be stored and that you can retrieve the energy, okay? So if I let go, all that potential energy will be going into kinetic energy, so I can get it back. In addition to that, any potential energy will involve a restoring force. It's not happy. Okay, it's not happy to be stretched. So there is a restoring force that wants to bring back the system to a lower level of energy. Nature loves the lowest level of energy as possible. Okay, so example, you have chemical potential energy, for example, in food. Okay, so if you are using glucose for energy, or if you are using ketone for energy, which is more efficient, by the way, you need this ATP, right, to have energy for your muscles. So how you do that? You're going to break the bonds. Okay, you're going to break the bonds. You're going to release this stored energy. This stored energy will go into producing ATP. So it's a long chain, right? So where it comes from? It comes from the electrons. You go from high level energy, electrons have high level of energy in glucose, for example, and then when you break those bonds, those electrons will go down to a lower level of energy, and that energy release, it's very complicated, very interesting, will go into ATP. Okay, but these are called chemical potential energy. It's in the bonds, right? Inside the molecules. So when you are burning fuel, okay, or if you are using an explosive, same thing, you are breaking the bonds, you are releasing that stored energy. More than chemical potential energy, you have nuclear energy. So that will be inside the bonds between the nuclei, okay, between the protons and the neutrons inside the nuclei. So nucleons, sorry, we say nucleons, right? So inside the nucleus, you have stored potential energy, which is called the nuclear energy. And when you break them apart, you're releasing mass, you are releasing energy. E equals mc squared. So after a nuclear reaction, if you measure the mass before and after, some mass has been lost. That's your potential energy being released. You have 1,000,000 times more energy in the nuclei that you have in the chemical bonds. 1,000,000 times more for the same mass. So if you are burning coal versus burning uranium, for the same mass, 1,000,000 times more energy. And then you have gravitational potential energy. Okay, so if I have a mass in my hand, okay, I'm doing work. All the work I have done is stored inside the bond between the book here, or the notebook, and the earth. So this is called gravitational potential energy. So you have to imagine this like something being stretched, right? So gravitational force wants to bring it back. It's a restoring force, right? So on Earth, like close to the Earth, the potential energy is just mgh. Okay, so if you decide that this is your potential energy equal to 0 here, if you want to find the potential energy of the notebook, you just multiply the mass times 10 times the height. So that will be the potential energy relative to the table. It's always relative to something. Okay, so the energy is stored into the configuration. And then you have elastic potential energy, which is 1/2 K. Next time, my back hurts. Delta X squared. Okay, so let's do a not so easy one. Okay, easy to be tricked. Here, number 3. So you have to be very careful. So the work done, let's do it this way, from x1 to x2. So that will be the force applied delta x. So that will be going from position 1 to position 2, okay, x squared over 2. So that's why you have to be careful. don't forget that actually it's an integral. So the work done by you on the spring going from x sub 1 to x sub 2, have to be careful because then you have to say that's going to be 0.5 k x2 square minus x1 square. So you have to be careful because some students, they want to do x2 minus x1 and then they square. Not so. Okay, so the work done will be 0.5. I didn't do it, so you do it. What? 300 and 300 and what? 309? 99.6. So that will be about 400 joules. Your unit is joule. Okay, so that will be the work done by you on the spring. And that will be the potential energy. So we're gonna have this notation here. Elastic potential energy. Yes. So similarly, when you do the change in kinetic energy, also you have to be careful. You're going to do 0.5, the mass, the V final square minus initial square. Don't go do final minus initial and square. So we have to do it this way. Okay? So make sure that as we go along, if you just want to take the MCAT, you do the problems that we covering the same thing that we are covering if you are going into mechanical engineering or physics or advanced engineering. You need to do the problems from your textbook because it's more, some of them are more advanced. It's good. Then it will make digestion easier when you take more advanced class with professors who are not that nice. I'm very nice, you know. Not all professors are nice. Okay, so potential energy will be so k x square, right? If you start from 0, initial position is 0, and you go to x, so then you use this equation. Agree? Okay, can you do something for me? Can you, and remember that the force that you need to apply is kx. That's Hooke's law. Agree? That will be also the restoring force. Can you do this? Can you derive the potential energy as a function of x? Take the derivative. What do you get? Kx, very good. Oh, wow. What does it mean? It means that if you take the derivative of potential energy, you get, so the restoring force is a minus here, right? So it's gonna be kx, so it's gonna be the restoring force, which is minus the restoring force in magnitude. So there is a minus. Minus, yes, because the restoring force is minus. So it's gonna be, so the potential, if you take the derivative, it's gonna be minus the restoring force. And that will be true not only for elastic potential energy, but for any potential energy, like the kind of potential energy you have in hydrogen molecule, for example. Okay, so that will be always true. So we say that the restoring force, okay, derives from potential energy. And this is a slope. See, it's the slope. So the restoring force is the slope of potential as a function of x. Okay? So any potential energy you have a restoring force. I want to bring back the system to a lower level of energy. It's called the restoring force. And how do you find it? You take the potential energy and you take the derivative. Or if you have the force, you take the integral. Okay. So restoring force is the derivative of the potential energy as a function of x, but it could be as a function of y and a function of z, so it could be in 3D also. So anyway, potential energy depends on the configuration of the system relative to a reference level. And the change in potential energy depends only on the initial position and the final position. Okay, so let's do something easy. Gravitational potential energy, okay, is just the weight, but that's easy to understand. If you take a mass in your hand, okay, the force that you need to apply so it doesn't move equals to the weight. You agree? Up equals down. Okay, so what I'm doing here, I'm doing work against gravity. So it will be my applied force, which is the weight, times the distance, which is just the height. So the work I am doing here, okay, it's going to go into the potential energy. I am increasing the potential energy of this mass. And the work is force, which is the weight, times the height, which is y in that case. Okay, so the work done on that mass by you, okay, will be the force applied, which is equals to the weight times the distance, which is just the height. And that will be the definition of gravitational potential energy. If you take the derivative here, what do you get? mgy. If you take the derivative as a function of y, mgy, take the derivative, what do you get? mg, which is the weight, which is the restoring force. So when you have potential energy, you take the derivative, you're going to get minus the restoring force because the weight is minus. The minus means that the restoring force wants to bring, if I let go, boom, to a lower level of energy. It's very important for chemistry. If you go to advanced chemistry, it's going to be very important to understand the potential energy of molecules. And okay, so let's do something super easy, super extra easy. Super extra easy. Extra easy. Let's do it. So it's always potential energy depends on the reference level, right? So it's always potential energy relative to what? Relative to what? Okay, so you have a table here, right? Are you doing it? Don't stare. I see people staring. Not healthy to stare. Do it. 3 kilogram. So relative to the table. So table here is 0.5. Okay, so the potential energy relative to the table here. So we say, okay, let's say potential energy equals 0 here. It's going to be mgh, which is 0.5. So the mass 3 times 10 times 0.5. Do you agree? So it's going to be what? 15 joules. Okay, and it's relative to the table. Okay, so it's always relative to some level, right? So that will be 1 meters. So this is 1 meter. So now we want relative to the floor, exactly. So this is 1.5 meters. So now potential energy here equals 0 here. It's always relative to something, right? So potential energy relative to the floor, so it's gonna be the mass 3 times 10 times 1.5, which is what? 45 joules. Thank you. Yes, you're right. 45 joules. Agree? And the restoring force in that case is the weight. Okay, mg. Okay, so the restoring force can say it's minus mg if down is negative. Yes. Yes. So the definition is this. So it's going to be mass times 10 times delta h. Because work done by you on the brick, okay, will be the force that you need to apply times the displacement, and the force that you need to apply equals to the weight. Okay, if you bring the brick from here to there, this is you here, mg, the force applied. Okay, if you move the brick up to this position here at a constant speed, the force applied equals mg. Up equals down. There is no acceleration, so apply force equals mg. Okay. Okay, so if you have two students, one takes the elevator and one goes stairway, but they have the same mass and they go to the same height. What is true about their gravitational potential energy? Same, very good. They have the same potential energy if they have the same mass, because it depends only on the mass and the height. Now, what is not will be equals. What is it that will be different between them? So the work done against gravity will be the same. What is not the same, of course, if you take the elevator, the time, very good, the time, which means power. So we're going to see that power is how fast energy is being stored, how fast energy is being consumed, how fast energy is being released. Okay, so the power will not be the same. It's the difference between the Bentley and the Hyundai, for example. So it's not the same power. How fast energy is being consumed. Okay, and then two important definitions. You have what is called conservative forces, so meaning restoring forces. So in that case, the energy can be retrieved. Okay, so weight is a conservative force, electric force is a conservative force, spring force is a conservative force, because I can always get back my energy. Non-conservative force meaning that you cannot get it back, you lose. So if you push this here along that path, or if you push it straight, it's not going to be the same thing. Here you're going to lose more heat. So the path you take matters. So these are called non-conservative force. However, if you take the potential energy, whether I go from here to there, or I go here, boom, 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 to the library and then come back to the same final position, the potential energy, the difference in potential energy will be the same. Okay, so potential energy depends only of the initial position, the final position. So it doesn't matter if I go straight from here to there, or if I go this and that, and go back to here, that will be the same potential energy being stored. Okay, so you can have two definitions here. So if you have a conservative force, that means you have potential energy. Potential energy only depends on the initial position and the final position. So if you go from here to there, or if you go from here, boom, 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 get to here, that will be the same change in potential energy. Okay. Now, if you go from here, so let me ask you something. What's the change of potential energy? If I go from here, go back to that place, zero. Very good, right? It will be the same potential energy. Yes. So if you make a loop, the change in potential energy will be equals to zero. Same potential energy, same initial and same final, so the change will be equals to zero. Okay, so that will be the definition. If you have a closed path, there will be no work done. Okay. Now we can have a more formal definition using calculus, right? So the change in potential energy, the change in potential energy will be the work that you have to do against the restoring force. So if you want to know the change in elastic potential energy, will be the work that I have to do against the restoring force. And that translates as this equation here. That will be the work done by you on the system. That work is being stored as potential energy. So the notation for potential energy is a uppercase U. So delta means a change. And you go from position A to position B, configuration A to configuration B. What matters is the initial position, final position, initial configuration, final position, configuration. In between, we don't care. Okay, so for example, if you have a potential energy here, and this is the electron, this is an electron. So that if you take quantum physics or quantum chemistry, even if you are in chemistry, you have quantum. I mean, all these orbital businesses has to do with quantum physics. They say quantum chemistry. No. It's quantum physics, right? Everything there is physics. So anyway, you're going to have an electron. An electron wants always to be at the lower level of energy. Okay, so when you are breaking bonds, when you are burning fuel inside the body, you see those electrons, they will go to a lower level of energy. That's the electron chain in the ATP business and the phosphate and things that I forgot. So anyway, always to lower level of energy. Okay, so for example, if an electron is here, which way it wants to go? This way, right? So if it's at E, it wants to go yes, very, very good, toward D. the restoring force is the slope. So what's the slope at D? 0. So it's happy. It's a stable equilibrium. If it tries to escape, boom, it's going to go back. If it tries to escape this way, boom, it's going to go back. Now here also, can you see there is no slope? Okay, there is no slope, but is it stable or unstable? Unstable, because if it moves a little bit, boom, it's going to go down. Okay? What is the largest slope that you can see between A, or maybe you have to B, C, D, and E? The largest slope of the roller coaster. No, A, the slope is 0. D is 0, the slope. B could be B or C, maybe probably B. E, I don't know. It seems to me that this slope is not as big as that one. It looks like B is larger. I mean, if you ask me if you want to ski here or ski there, I will say there, or I will say here. Right. So the largest slope might be at B, which means the largest restoring force that the electron will experience. So if you have potential energy as a function of position, the slope is the restoring force. Okay, so if it's there, it wants to move this way. If it's there, it wants to move that way. Okay, you survived. It's a lot of application in chemistry. So maybe did you take this advanced class? It's called the Lennard-Jones potential. It applies to very simple molecules. So if you have two hydrogen atoms and you have a hydrogen molecule, hydrogen gas, there is the distance between them. It has to be ideal. So if you move them close to each other, it's not going to be happy. You're going to have a repulsive force. If you try to bring those two atoms of hydrogen apart, you're going to have an attractive force. And you can show that with this diagram, that this because those two hydrogen atoms will have the lowest potential energy at this position here. Right? Gas, simple fluid. Yes. So you store energy into hydrogen bonds as well. Okay. Taking a tangent, the gravitational forces between two masses, so that's Newton's universal gravitational law he came up with because he was a genius. So between two masses, you're going to have an attractive force, okay, that will be proportional to the masses. So proportional means when you translate that with math, it means you multiply. Multiply M1 by M2 because we don't want to have favoritism. Okay, M1 and M2, there is no reason M1 should have a square, not M2, so M1 times M2. And inversely proportional to the distance, obviously, because when you move those masses apart, the force will decrease. That makes sense. But it's inversely proportional to the square of the distance. So this is called the inverse square law, which means if you multiply the distance by 2, the force is divided by 4. If you multiply the distance by 3, the force is divided by 9. Opposite? Opposite. Yes, so it's not proportional to the square, you're right, it's inversely proportional to the square. If you divide the distance by 2, the force will be multiplied by 4. And that's how your weight works. So if you take the Earth, so this is the Earth here, so that will be the center of the Earth. This is the radius of the Earth. It has a big mass here, and this is you here. You have a small mass. Okay, and let's say your mass is 400 pounds. Not you, a truck, or something. Maybe not a truck. 400 pounds. A motorcycle. Thank you. Okay, so a motorcycle. Okay, so it's a motorcycle. I don't know how to make like a motorcycle. Okay, if now I take this motorcycle into orbit, okay, this is just m. Okay, so the mass will be the same, but now the distance here, let's say it's 2r. Okay, so twice the distance, because this is r and then r. What's going to be the weight? 100 pounds. The mass will be the same, but the weight will be divided by 4. So here, that will be the weight, and here the weight will be 4 times more. 1, 2, 3, 4. I mean, you get it, right? It's not very nice. So if you take the same motorcycle, okay, I'm going to try to do better. 1, 2, 3. So that motorcycle is in space. So distance is 3r. What's going to be the weight? It's going to be 400 divided by 9. Which is what? 44? Thank you. 44 pounds. Agree? So this is called the inverse square law, and it will apply to any field. Electric field, for example, light, electromagnetic field. So before I get to that, you see the force here, so it's proportional to the product of the masses, inversely proportional to the distance square between the masses. So it could be the Earth and the Moon, or it could be the Sun and the Earth, or it could be, I don't know, Mars and its moon. Okay, so anything with masses, they attract each other. How come we are not stuck with each other, right? Because here you have a constant, so that will be called the gravitational constant, and it's super, 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 super extra small. So it's 0.0000000000667. So very small. So that's why you need something huge to experience gravity. Okay, G is very, 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 very small. And G was not computed by Newton. He found the equation. It was a very famous Cavendish experiment. Okay, you can look it up. He did the experiment to find G, to find that constant. By finding the constant, he find the mass of the Earth. If you have that constant, you can find the mass of the Earth. He weighed the Earth in a way. Okay, is that clear? Microphone is never good. Okay, so that force here, so this is me. Yeah. So that force will be G 6.67 times 10 to the negative 11 times my mass times the mass of the Earth divided by R squared. Do you agree? So the force that the Earth is acting on me is equals to my weight. Okay, so that's going to be equals, so my weight will be 6.67 times 10 to the negative 11 times the mass of the Earth times the radius of the Earth square times my own mass. Do you agree? Okay, try to compute this. So the mass of the Earth is 5.972 times 10 to the 24. That will be the radius of the Earth. So try to do that computation. 6.67 times 10 to the negative 11. Do it. Don't stare. The mass of the Earth, 5.972 times 10 to the 24. Is that right? Okay, divided by the radius, so it's 6,000 kilometers, so 6371, convert to meters, 1, 2, 3, you square, what do you get? 9.8. Yeah, we get the acceleration due to gravity, we get the 9.8, okay? So you find the weight on Earth is mass times 9.8, okay, and that 9.8 is this. So it will change if you go to Mars. If you go to Mars, I forgot, it's going to be something like 3.7, something like this, I forgot. But if you go to Mars, it's going to be smaller because the mass is smaller. So it depends on the size and on the mass. Agree? Isn't that cool? And so Newton was he was a sociopath, but he was a genius. You have to give credit where credit is due. He was really a genius. So where does it come from? We can understand the inverse square law by looking at 3D geometry. So it's called solid angle. I don't know if you learned that in geometry, solid angle. Imagine this is light. So light will also obey an inverse square law. So let's say you have light here and you have a sensor. So this here you have a source of light in 3D. Here they just focus on this, but it's in 3D. It could be a star. So you have a star here. It could be the sun. Let's say this is the sun. So you have a sensor. This is how much light you're going to get here. Square unit. If you multiply here the distance by 2, the same light will spread out over 4 times the area. Can you see that? The same light. So the thickness will be divided by 4. If you multiply the distance by 3, the same light will spread out over 9 times the area. So the layer, if you think of the photons, the number of photons that you collect here will be divided by 9 per unit area. Exactly. And this is called a solid angle in geometry, right? So that's why you can do that with someone. Student did a silly experiment. He took a butter spray, which is very unhealthy, but like at a given distance, you spray your French toast, yeah, and then you multiply the distance by 2, and you need 4 toasts. You need 4 toasts, right? So 4 times less layer will be divided by 4. See what I mean? And it's, or you can do that. I don't know why butter. I don't know why he chose butter, but you can do that with paint. So you have something like this. That will be 1 toast, French toast. Actually, in France, we don't eat French. I don't know why it's called French toast. It's not French. French will eat baguette, as you all know. 2, 3, 4. Not bad. And this is healthy butter. No. Just for experiment, right? This is not healthy. Okay, so then the question is, okay, so far we have seen if we don't move far away from the Earth, okay, then G is constant, it's about 10. But as you move away from the Earth, G will depend on the distance from the Earth. So in that case, the force of gravity will be at a distance r. So if you are on the Earth, the distance is the force is mg. Do you agree with me? If you are on Earth, the restoring force is mg. Do you agree? As you move away from the Earth, the restoring force is going to decrease. Yes? So if you want to find the potential energy, remember what I told you before? The potential energy is a restoring force derived from a potential energy. So if you want to find the potential energy, you just have to take the derivative. This is R. Okay, that comes from here. I mean, that will explain that, except you have a dot product. So I'm not going to do the computation, but you see that if you take the integral of 1 over x squared, you're going to get 1 over x. Agree? So if you take the integral of 1 over r squared, you're going to get 1 over r. So the gravitational potential energy is this expression here. It's inversely proportional to the distance. You have a minus here. So that's the formal definition of the gravitational potential energy of a mass located at the distance r from the center of the Earth. So if you have a mass m located at a distance r from the center of the Earth, so you take from the center of the Earth, that will be its gravitational potential energy. That will be the mass of the Earth. And you have a minus because it says it's binding. It's binding. It wants to bring the mass to a lower level of energy. It's binding. So it's trapped. So if you want to escape the Earth, you need to put fuel. You have to work against gravity. Okay, so gravity is like a restoring force. So if you want to escape, you really have to do some work. So the minus means it's binding. Okay, so that will be the equation for the gravitational potential energy of a mass located at a distance r from the center of the Earth. And then a little bit of math. So if you do potential as a function of r, you get that equation here. So that will be just minus 1 over x. You see, minus 1 over x, that will be minus 1 over x. So as you move away from the Earth, at some point, very, very far away, the Earth cannot reach us anymore, right? You are so far away. It cannot reach us. It cannot reach you. So in that case, the potential energy will be equal to 0. And at infinity, there will be no more force from the Earth. You escaped the Earth. You are very far away, and the potential energy equals to 0. And as you get close to the Earth, right, it's going to be more negative because it's going to be more binding. So here you increase the potential energy, and then if you let go, zoom, it's going to go all into kinetic energy. So that's just a stretch. You don't have to worry. I mean, you just have to worry about this equation. Yes. Yes, but it should be in the equation sheet. It's not. It's going to be for test 3. So you don't. And test 3 is open book. So you don't. But it should be in the equation sheet, right? So that will be the gravitational potential energy. That will be the gravitational force. The idea is that potential energy is binding. So you have to fight against the restoring force if you want to escape. So you see this inverse square law. If you are doing photography, for example, uh, you can use it, right? You see the amount of light. If you are using projectors, and why not? You see, you multiply by 2 the distance. The amount of light here per square unit area will be divided by 4. If you are doing red light therapy, okay, if you are working physical therapy or I don't know, wellness stuff, okay, it applies also infrared therapy, inverse square law, so you can understand how much you are getting as a function of the distance. Security check required. Verifying. But you learn that, okay? So maybe you want your patient to get that much of radiation, red light, infrared, which is very healthy and safe. You see, the light that they will get on their skin depends on the inverse square of the distance. Uh, Red light, maybe. So here it is. You see. Okay, you can do the computation here. You see, at that distance here, you're gonna get less red light. So maybe you want to adjust depending of what you want to get. Um, radioactivity. Radioactivity is also obeying the same law. So when you have a isotope, radioisotope breaking down, if you multiply the distance by 2, you will get 1/4 of the radiation. So when this accident happened, when they were making the atomic bomb, the plutonium bomb, there was this accident, very famous accident. You know, he was working like a very young scientist, very enthusiastic, not very careful. They were working on the core of the bomb, the plutonium bomb. So you had bricks all around to protect, and then a brick fell, and the guy sitting next to the core, and the chain reaction started to happen. So you had all those radiation going into in 3D in space, right? So he was exposed to a huge amount of radiation, but his colleagues who were further away, because of the inverse square law, they didn't die. Because you multiply the distance by 2 and divide by 4, you multiply it by 3, divide by 9. He was the only one, the first one to die from radiation sickness. You can read about that story. It's a terrible story. Because radiation sickness, you don't have time to develop cancer, you just die. I mean, it destroy all your cells. It's like chemotherapy on steroids. You lose your hair, the guts is done. Terrible way to go. And he was so much into science that everything he had experienced, he wrote it down. Right? He wanted to tell people what's radiation sickness, not radiation therapy. Did I say radiation therapy? Sickness, radiation sickness. Yeah, you die from radiation sickness in a few days. It happened to a spy. Do you remember that spy? He was working for the Russian and he was working for the British. So they, I don't know, maybe the Russian, we don't know, put some polonium in his drink, and he died of radiation sickness in a few days. To make the point, it's a very famous story. So anyway, radiation sickness is not cool. They had to bury him in England in a coffin, a special coffin. So much radiation was coming out of his body. So I don't know why I'm talking about radiation sickness, but okay, let's. Okay.